My name is Jordan Olmstead, and this is my video assessment for Physics 192. So for my video assessment, I chose question 38 from chapter 20. The question reads, the primary coil of a transformer has 250 turns. The secondary coil has 1,000 turns. An alternating current is sent through the primary coil. The EMF in the primary is of amplitude 16 volts. What is the EMF amplitude in the secondary? So we know that transformers have two separate strands of insulated wire. The magnetic field lines are guided through an iron core. So the two coils, there's a primary coil and a secondary coil, enclose the same magnetic field lines. So the equation for the primary coil is EMF1 equals negative N1 times the rate of change of the flux through each turn of the primary coil. Now, N1 or N2, N in general, is for the number of turns that occur. So N is just the number of turns that there are. Now, the AC current, so we know we have an alternating current based off of the problem, and the AC current in the primary coil causes a changing magnetic flux to the secondary coil. And so that equation that I just said, EMF1 equals negative N1 times the rate of change of the flux through each turn of the primary coil, comes according to Faraday's law. And so we also can look at the secondary coil and get the equation EMF2 equals negative N2 times the rate of the change of the flux through each turn of the secondary coil. Now, the flux through each turn of the primary coil is equal to the flux through each turn of the secondary coil at any point. So, therefore, we can take the rate of change of the flux out of the two equations I just said, because it is the same quantity in both of them. Therefore, when we eliminate the rate of the change of the flux, we end up with the ratio that I have written on my paper that I used for the problem. EMF2 over EMF1 equals N2 over N1. So that is where that equation comes from. And based off of this equation, this ratio that we have, and the ratio of N2 over N1 is actually called the turns ratio, we can solve for the EMF amplitude in the secondary coil. Now, I went ahead and plugged in my given variables. The problem tells us that N1, the primary coil, has 250 turns. That's N1. The secondary coil has 1,000 turns. That goes in for N2. We see that the amplitude of the primary coil is 16 volts, so that can be plugged in for EMF1. And we are looking for the EMF amplitude in the secondary coil. Now, in order to find EMF2, we have to isolate the variable. And in order to do that, we have to get rid of the 16 volts on the left-hand side. And by doing that, we're doing division. The problem is calling for division, so we multiply by 16 voltage to cancel the 16 on the left-hand side to isolate EMF2. And whatever you do to one side, you must do to the other. So we multiply 16 voltages on the right side. And that leaves us with EMF2 equals, I went ahead and divided 1,000 turns by 250 turns and got 4. So we get EMF2 equals 4 times 16 volts. And then I went ahead and multiplied 4 times 16. And we get that the EMF amplitude in the secondary coil equals 64 volts. Now, based off of this information that we just solved in this problem, we can actually see that this transformer is a step-up transformer. We know this because whenever the voltage goes from a low voltage to a high voltage from the primary coil to the secondary coil, it is a step-up transformer. So we see from the primary coil to the secondary coil, the voltage goes from low to high. Therefore, this is a step-up transformer.